So in this video, we're going to go over how to track a source of error through your calculation so you can figure out if your calculated result is too high, too low, or would it remain the same. So I'm going to walk through this example, which is from my class in our note packet, which mirrors a lab that we did on precipitation. And here we're reacting this XCl, this unknown chloride. There's 40 grams of it. We're reacting with lead-2 nitrate to form a precipitate, and 74.6 grams of this precipitate was collected. So what is the identity of X, which we can get through calculating molar mass? So I'm going to take a moment, run through those calculations first, and then we'll talk about error. So here's a reaction that relates XCl with the lead-2 nitrate, the reaction between them. I notice that I have a double replacement, X and PB switch places, and I get PbCl2 as one of my products. PB goes with Cl, and XNO3 is my other product. And because it tells me there's a precipitate, I should know that ammonium nitrate and group 1 are always soluble. So XNO3 can't be my precipitate. It has to be PbCl2, which is my precipitate. So this 74.6 grams is of the PbCl2, which is great because I know the molar mass of that, and I've essentially changed something I don't know, XCl, into something I do know. So I can take that 74.6 grams of PbCl2, divide by the molar mass, and I would mole out my PbCl2, which I can then relate to the XCl through stoich and say, hey, there's a 2-to-1 mole ratio, and turn this into moles of XCl. And this is the moles of XCl that I reacted. Now, what's great is that I have the grams of XCl that I already weighed out. So as long as that XCl is the limiting reactant and it all got turned into the PbCl2 and all got used up, then that 0.537 moles of XCl and the 40 grams of XCl are equivalent. They are the same value, just different units. And when you have grams and moles of the same quantity of the same thing, we can calculate the molar mass, because if we divide grams by moles, then we will have our units of grams per mole, which is the unit of molar mass. We just had to make sure that XCl was limiting and not in excess. And now I have my molar mass. I can figure out what XCl is by subtracting out the molar mass of the chlorine, which is 35.5, and I can see that X has a molar mass of 39, which is potassium. So now that we've run through these calculations, let's take a moment and analyze sources of error that could be in this experiment that would affect my calculated molar mass. And we can answer questions like, is this calculated molar mass 74.5 grams per mole? Is that too high, too low, or would it be the same if certain sources of error were present in the lab? So when you're tracking through a source of error in an experiment, it's really helpful to have your calculations out in front of you so you can figure out what number is being affected. And then you can track that number through your calculations and see how it's impacting your molar mass. In this scenario, your molar mass is what you calculated. Is your molar mass too high, too low, or would it remain the same in these different sources of error? So let's say your source of error was that your precipitate was wet, meaning it absorbed some water into it, whether it just wasn't fully dried, or maybe it's hygroscopic, meaning that it absorbs water into the structure. But any which way, let's say that this 74.6 grams of precipitate not only included the PbCl2, but also included water. And the question would be, how is my calculated result? How is my calculated molar mass of 74.5 grams per mole? How is that impacted by this error of including water with my precipitate? Is that 74.5 grams per mole too high, too low, or would it remain the same even if this source of error occurred? So what you do first is you need to find the value or measurement that is affected by the error in your calculation. So you always go to your calculation and find the source of error. In this case, it is this 74.6 grams of precipitate that is affected by this error. If I've included water in with the precipitate that I weigh, this 74.6 is too high that I've measured in the lab because it not only includes PbCl2, it's wet, so it also includes water. This number should be lower, but it's too high because I inadvertently also have included water and didn't realize it because it's either hygroscopic or I forgot to finish drying it all the way. Whatever the case, that number's too high. And now I can track this number, track this error through my calculations, and I see that if that 74.6 is too high, then the moles of XCl that I calculate are going to be too high, should be lower. And then this denominator is too high. So when I calculate the molar mass, I'm dividing by a number that's too high, and therefore this molar mass is too low. This error of having more water in the precipitate has resulted in a molar mass that is too low. It should be higher. And I like to talk in terms of too high, too low, because I see it phrased like that on the AP exam a lot. But some people, it clicks more of should be higher or should be lower, and it's really the same thing. So if this precipitates too high, it means, hey, it should be lower. This 74.6 grams includes not only PbCl2, but also water. So if that should be lower, then XCl2 moles calculated should be lower. This denominator should be lower, and the molar mass that I calculate based off of this should be lower denominator should be higher. That is the exact same thing. Saying something should be higher is saying that my calculated result as is too low. So it's the same exact terminology. You can use whatever you feel comfortable with. I'm going to use too high, too low a lot more often because that's what I see asked on the AP exam. But no matter what, you find the thing affected and you track it through your calculations and see the result on your final calculated answer. Okay, let's try another source of error. Let's say the source of error is that not all of your precipitate was collected. You've lost some along the way. And that might mean that some of it wasn't collected in the filter paper. And it kind of makes sense if you think about the lab. Sometimes you saw some of the precipitate left behind in the glassware. It might have mean that you spilt a little and some did not all get collected on the filter paper that was weighed. And the question would be, how did that impact your molar mass? If that indeed happened, is your calculated molar mass too high, too low, or does it remain the same? Give it a shot and then check my answers. So if this was not all collected, this 74.6 grams of PbCl2 is actually too low. More should have been collected, but we lost some along the way. So this value, 74.6 that I'm plugging in, is too low of a number. It should have been higher. So if I go through my calculations, if that number's too low, then that means the moles of XCl2 that I calculate here is too low, which means my denominator here is too low, and therefore my molar mass is too high. This calculated result is too high, 74.5. I should have gotten a lower number. And again, you can use this terminology, too low, too high, or you can say, hey, this should have been higher. If I lost some along the way, the 74.6 grams should have been higher. And if that should have been higher, then this moles of XCl should have been higher, which means my denominator should have been higher, which means this molar mass should have been lower. Again, that's similar to saying this value is too high. Same terminology or same logic. It's just different, slightly different, saying should be's versus it is too. So let's try another source of error. This time, let's say, let's take the focus off the precipitate for a moment. Let's say that not all of the XCl2 reacted, meaning that maybe some was in excess and didn't get all used up, meaning that maybe you lost some when transferring, when weighing it out and transferring to your beaker, meaning maybe some of it was left, didn't dissolve and therefore didn't react. But no matter the case, this 40 grams of XCl did not fully react. So try the source of error, see how it would affect your molar mass. Is this molar mass that I've calculated too high, too low, or would it remain the same? So if this is your error, where your XCl did not fully react, then essentially you can think of this in two ways. You can say that, hey, the number that would be affected is this 40 grams because this number is actually too high since not all of it reacted. I either lost some along the way or there was some excess in the container. If that number's too high, it's in the numerator. So that means my calculated result, the 74.5 grams, is too high of a number because this 40 grams was impacted. Now, some people, and again, saying that 40 grams should be lower, this should be lower is the same as saying too high. Now, some people might have said, wait, I'm going to, instead of looking at the 40 grams being impacted, I'm going to think of it as a different way. I'm going to say that if some of it didn't react, then that means that this 74.6 grams of precipitate is actually too low of a number. I should have gotten a higher value if all of the XCl reacted, but since it didn't, that number is too low. I could have formed more precipitate but didn't. So if this number that I'm plugging into my calculation is too low, should have been higher, then that means my moles of HCl is too low, which is in my denominator. And if that denominator is too low, I'll be dividing by a number too low. So therefore, this molar mass is too high. It should have been lower, which is the exact same result as I got by examining the 40 grams. Sorry for that scribble. So what I mean to say is that sometimes a source of error can affect more than one thing in a calculation, and it really shouldn't totally matter which way you think of it, like in this case, whether I tracked the 40 grams and saw the effect or whether I tracked the precipitate and saw the effect. The effect was exactly the same, that my molar mass was too high as a result of this error. So whether I looked at the 40 grams or the mole amounts, I got the same answer. So you don't necessarily have to explain it both ways. Whichever way clicks with you more, feel free to go through. But again, same thing results. You're tracking the number through the calculation and seeing how does it affect your final answer. And I love to write these little too highs, too lows things on my actual calculation. So don't forget to go to your calculation. Let's try one more source of error. So let's say this HCl that you weighed out actually had some water in it. So whether it was wet or hygroscopic, it absorbed water, or maybe it was a hydrate and it actually had H2O in the structure and you weren't aware of it. You thought it was just pure HCl. How would that impact your molar mass? Is your molar mass now too high, too low, or would it remain the same for this calculation? So try it and check your work. So if this HCl actually had some water in it, then I would say the number affected is this 40 grams of HCl, because it really doesn't only include HCl, it includes water. So this is actually an overestimation of how much HCl you have in your container or that you're reacting. This number is too high. It should be lower if we're talking about pure HCl. This 40 grams is not just HCl, it's also with water. So if this number is too high, then my molar mass is obviously, since this is in the numerator, my molar mass is also going to be too high or should be lower because of this. Again, I'm just tracing through my error, through my calculations. If I had weighed that 40 grams without the water in it, it would actually have a lot lower of a number of grams of pure HCl. So this is just an example or a few examples of how to find how your sources of error impact your calculated results. Let's now take a look at a titration example because that's another type of example that you see sources of error asked about. And this is an example from my note packet, but it kind of relates to a titration lab that we've done in my class too, and maybe relates to one that you've done. So here's a titration example. We are exactly reacting. We have the known molarity of nitric acid. We're figuring out what volume is needed to react with and fully neutralize a 50 milliliter solution, 50 milliliters of calcium hydroxide solution. We don't know the molarity. We are asking what is the concentration. That's what those square brackets mean. What is the concentration of CaOH2, the molarity of it? Now, you can solve these titration problems multiple ways. Some people like to use stoich. I tend to use this little shortcut equation because it's derived from the fact that the moles of H plus have to cancel out with the moles of OH minus as long as both of those reactants are used up. And so the MA and VA is a way of moling out your acid, and then multiplying by the number of H's will turn it into the moles of H plus. So if it's like H2SO4, you'd be multiplying by 2. And then the molarity times volume of the base gives you moles of the base. Multiplying by the number of OHs turns it into moles of OH minus. So this equation comes from the fact that the moles of the H plus have to cancel out with moles of OH minus. And if I plug into this from my from what's given here, just make sure everything on the acid side goes on the left. There's 1 H plus for nitric acid, so there's a 1 there. I put my volume, I put my molarity. I'm solving for the molarity of the base. I'm given the volume of the base. I'm multiplying by 2 because it's calcium hydroxide. There's 2 OHs, and I can solve for the molarity of the base, and I get 0.034 molar. And again, you might have solved for this using stoichiometry and writing a reaction between the calcium hydroxide and the nitric acid, and you'll notice that there would be a 1-to-2 ratio because there's 2 OHs and 1 H, and that's what that number of H plus and number of OH minus in this equation are accounting for. So again, you might have solved it a little bit different, but now that we have our calculation, we can go into our calculation and trace any source of error. So let's do that. So let's talk sources of error. Let's say in this burette of nitric acid that you're using, that you've actually have some water droplets in it before you filled up with the nitric acid. How would that molarity of the base been affected by this source of error? So if you did have water droplets in your burette, then essentially that molarity inside your burette is no longer going to be the 0.0980 molar that you've seen on the bottle that you've used to take a sample of the nitric acid. If you have water inside the burette, it's going to dilute that acid. And if I dilute that acid, then we are no longer going to have a 0.098 molarity. It's going to be a lot lower. And however, when I'm going into this calculation, I am not putting that diluted molarity down. I am writing the 0.0980 that you find on the container, even though the burette is more diluted because of water being left behind, because maybe it wasn't rinsed properly. Remember, in the lab, you're supposed to rinse with the solution you're titrating with. So if the source of error is that you have accidentally diluted this acid, then this molarity that you're plugging into the calculation is too high. And if this number is too high, notice it's going to be in the numerator of whatever you calculate for the molarity of the base. And if this number is too high, because I'm just reading what the bottle said and it's not accounting for the fact it got diluted in the burette, then this number that I've calculated is too high. So the molarity of the base that I've calculated is too high. It should be lower. It should be lower because the molarity of the acid was actually diluted. And this is a great way of tracking error. You go to your calculation, you find the number affected, and you see the result. Now, you can actually think of this in another way. Rather than saying that the molarity of the acid is the thing affected, you might have thought about it as the volume of the acid being the number affected, and you would get the same answer if we think about this. If you did, in fact, dilute that burette, and it no longer has 0.09 molar solution, but is more diluted than 0.098 molar, then this volume is actually too high because I've used a diluted solution, and therefore I need more volume of it to get more moles of the acid reacting. Had I not diluted it, that volume should be lower. I would have used less had I had a more concentrated nitric acid that wasn't diluted. So I could see that this volume is too high. How would that impact my molar mass? That's in my numerator. I'm not dividing by it. So this would be too high of a calculated molar mass. It should be lower had I not diluted the nitric acid by having those water droplets left in the burette. So notice that whether I'm thinking of it in terms of the molarity of the acid or the volume of the acid, I've resulted in the same conclusion that this calculated molar mass is too high or that it should be lower, which means the exact same thing. And if this is a free response question and you have to explain your reasoning, you could have explained it either way, usually as long as you get the answer of too high, too low, whatever that is the exact answer, and you explain it in some sort of way that makes sense or isn't wrong, you would get full credit. Let's try another source of error. Let's say that the 50 milliliters of the CaOH2 is transferred to a flask. And the nitric acid is what's in the burette that we're adding drop-wise. But the base is being put in a 50 milliliter flask under it. And let's say before we even put the base into there, we measured it out with a graduated cylinder, pardon my really terrible drawings. But we've measured out the 50 milliliters of base, we transferred it into the flask. However, the flask that we transfer it into had some water droplets in it before we transferred the base into it. What would be the effect on your calculated molarity? Is it too high, too low, or would it remain the same? Try out and give me your answer and check your work. Now, if the water droplets were in the flask, it should not impact my molarity at all because I've already transferred all of my moles into the flask, and the water droplets that were there were not impacting my moles transferred. Now, if there were water droplets in the graduated cylinder when I measured out the base before pouring it, that would dilute the molarity, and there'd be less moles of base transferred into the flask. So that would affect it. But as long as the 50 milliliters was transferred appropriately, if there's some water in this flask, yeah, it would dilute the molarity in there a little bit, but it has no effect no impact on the moles of base transferred, and therefore everything would be the same. If I go to my calculation, I still measured out 50 milliliters of base. That's okay. I haven't done anything in terms of diluting the acid. I would still need the same volume and of the same molarity of acid to cancel out all the moles of base that I've transferred. And so nothing would change in this calculation, and my calculated result would stay exactly the same, even if there were water droplets. As long as there's no water droplets in something that's actually transferring, something that's where I'm actually measuring the volume of the base before I transfer it there, that would impact it. But just putting it in the container where the reaction's happening, having some water in there, is totally fine. And if you remember from the titration lab, we even did that. We added some squirts of water into the beaker just to have a little bit more of a swirl to it, because it didn't affect the moles of acid or base. It was just in the reaction vessel. So hopefully this helped you track sources of error through your calculations. I have a video on tracking sources of error through a collecting gases over water experiment, which you can feel free to watch if you still need help with this when you get to gases.